Welcome back to Further Systems of Equations. I hope you've been enjoying yourself solving those interesting systems we had a look at in part one. And we're going to have a look at an interesting setup here where we have, let's say, a planet with an elliptical orbit, and we have actually spotted it on a grid system at several points. Can we describe the overall path of that planet and thereby predict where it's going to be at certain times? Well, over here we have the general equation of ellipse in that situation, and just remembering an ellipse, this is not really part of this course. It's actually a conic section. If you take a right circular cone there, let's finish it off here. Let's make that a little bit better, I think. If we took a right circular cone, which would be like this, and we slice it, section it, at an angle to the base there, we produce an ellipse, and other shapes you can section in various ways. So this ellipse is actually called a conic section, a section of a cone. So if it has this equation, maybe if we had all these points over here, we've got, 5 of them, and we substituted those x values and y values in place of x and y in the equation, maybe we could find the unknowns here and thereby complete our equation and find the actual equation of the path of that planet and predict where it's going to be at certain times. So that's an interesting one. We're actually going to solve this system later on. That's a 5 by 5 system. I guess you're thinking, oh no, how many zeros do I have to get down the bottom there to solve that? But we might do that one a different way. And we've got a few others here, just like we were looking at before. Hey, this bottom line's interesting. Hey, so is this one. I wonder what that means. Just remember now, rows are equivalent to equations in an augmented matrix. So I wonder if you can make any sense of the bottom lines of these two. What might they mean? And then, of course, what about this? We've got 3 unknowns. This is a 2 by 3 system. All right, 2 equations and 3 unknowns. I don't think we've got enough information, have we, to solve for x, y, and z there if we've only got 2 equations but 3 unknowns. Are you getting the idea here of how to solve a system and what restrictions there are if we only have 2 equations but 3 unknowns? Anyway, we'll come across that as we go on. So this is an exciting part. We're going to go to the next level now. So what I'd like you to do is come down with me now and let's have a look at other 3 by 3 systems. Now again, we're using the textbook from Hayes and Harris, so it'd be good to have that and check through it as we go. The presentation here is slightly different, but basically follows the book. So we've got a 3 by 3 system, and we're looking to see if there's a unique solution, that is 1x, 1y and 1z, that makes all 3 equations balance or equal the numbers on the right side together simultaneously. Obviously, there may be no solutions, no particular x, y and z that works in all of them. Just remember, no solutions means there is no particular value of x, y and z that works in all of them together. Or there might be infinitely many solutions, as we saw in the 2 by 2 system, where, for example, if 2 lines were coincident and lie on top of each other, there'd be an infinite number of solutions. So let's have a look at this system here. Again, let's make an augmented matrix. We're making a matrix. Just remember now, a matrix is an array of numbers, is an array. It's a pattern, and we've detached the coefficients, the important numbers here, out of the equations. And just remember now, in the augmented matrix, rows are equivalent to equations here. Okay. All right, so let's start the process. We're going to start with a 0. We're trying to get a 0 down in that position. So we're getting row 2 minus 2 row 1. Can you see that? There's row 2, and if we take away 2 times row 1, it will work. Here's a working here. Here's row 2, and they've got adding on neg to row 2, neg 2 row 1, and there we have the 0 appearing. These working steps are important later on when the going gets a bit more difficult. And now we want a 0 in this position, so we say into row 3, we'll have row 3 take 3 row 1. So there's row 3, and here's take 3 row 1. Because up here, come back up here, we've got a 3. If we take away 3 times 1, that'll give us a 0. So this idea over here of having a 1 up in the top corner can be quite handy. We'll see that later on as well. We produce that other 0. Now, I'm strongly suggesting that you don't do these 2 steps at once like this. I suggest you do the first one, write down the equivalent matrix. Remember that there is equivalent to or has the same solution as. Right, I'm suggesting you do that first, then that one stage at a time so you don't mess it up in the harder problems. So let's come down and finish it off. So now we need a 0 in this position. So what do we see here? Well, it's going to be row 3 minus 2 row 2. Notice at this stage we can only play with these 2 rows. If we bring in row 1, it's going to disturb these zeros. So in that last stage you're looking at manipulating row 2 and row 3 to get that 0 without losing any of these zeros. Alright, so working out again, give it all a tick. The interesting thing here, of course, is this bottom row. As I mentioned back at the beginning of the presentation, what does that bottom row mean? Write it out. 0x plus 0y plus 0z equals 5. Which is impossible. They've said absurd, I prefer impossible, which is impossible, therefore the solution the system has no solution. We often use the word here, it is inconsistent. In other words, it is not possible to have a consistent solution working for all 3 equations. So write out the equations, rows are equivalent to equations in augmented matrices. So write it out so you can keep touch with what's going on. A lot of people with this work start to think, well, it's just a set of numbers. No, don't forget the roots of the system here. What we're using is an augmented matrix system to solve a solution, or get a solution, or solve a system of equations. Okay. Using a graphics calculator, well, I don't think you'd go to the trouble of entering that in the graphics calculator. If you want to use technology, I'm suggesting, of course, you use Equimode on the Casio. So in here in Equimode, this is Equa, I haven't put all the screens down, Equa simultaneous, and you want 3 unknowns. Going in there, you'll enter the 3 equations, and if you try to solve, it tells you there's a maths error. In other words, mathematically you cannot solve it. It means therefore there is no solution to this set. Alright, so that's an interesting one there, and we'll see how we go now as we go down into the next one. Let's have a look at this one. Again, just a set 3 by 3. Here's not a bad idea, as I said in the previous working there, that we would have the second equation on the top line, so you get a 1 up here. So it's easy to refer back and use it to take away the value that you want. So we want a 0 here, let's say, first of all. So we want that 0, so it's row 2 minus 2 row 1. Here it is up here, the working out. Now we want a 0 there, so let's look at it. It's row 3 minus 3 row 1. Getting the hang of it, there it is there. I would suggest you split these steps, split into 2 single steps, and do them one after the other, not all together, so you don't get confused. It gets harder a bit later on. Okay, so now we want a 0 in here, so looking at the neg 6, it'll be row 3 minus 2 row 2. Okay, so here, we've got row 3 is neg 6 and 2 times row 2. Now, just what we want to check that there, don't we? Because here we've got row 3, yep, that's okay. Row 3, 2 times row 2 up here, yep, that's good. We've got neg 2 is plus 6, yep. So that's good, neg 2 times row 2. So there we have it, we get all zeros. Now, what does that mean? Oh, well, let's write out the equation. 0x plus 0y plus 0z equals 0. In other words, x, y and z could be anything, couldn't they? Because 0 is going to equal 0. With all these zeros, going to give you 0 equals 0. So it's not saying anything. It's not actually, this equation is not contributing any more information to the system. So what we say is, well, let's stick anything in there. What's an anything? Well, let z equal 2. And if you substitute that back now, you know the process, substitute it back into row 2, we get this result, and then sticking them both back in row 1, we find that's the answer there. So what does it mean? What does it actually mean? Well, what it means is, if z is anything, right, if z is t, then x will always be 7 over 3 and y will be neg a third plus t. So there is a pattern to the solution. There's a pattern. We haven't lost everything. There's a pattern to the solutions. So I'm putting plural now, because what we've been able to say is the last equation up here doesn't contribute. No info coming from the third equation. But what about the other two? They're still describing to us a pattern between the possible x, y's and z's that will work in the 3 by 3 system. We have seen that anything will work in the bottom equation, so that gives us the idea there's many solutions. So if we put a t in there to represent any value and back substitute, we do have a pattern for the solutions there. Okay, so the interesting thing here is that you might try that on the calculator and see what that one brings up when you have 0, 0, 0, 0 all in the bottom line in equimode. All right, are you ready to have a go yourself? This is getting interesting, isn't it, to see how it all comes out. Please remember, don't get confused. Here we have developed an augmented matrix to do this. Rows are equivalent to equations. If you ever get stuck, go back and write it out and look at the thing. Okay, look at the thing. 0x plus 0y plus 0z equals 0. Hey, that's telling me nothing. This is not hard mathematics, but it is if you just think of the augmented matrix as a whole heap of numbers. Oh, no. They represent equations. Okay, come down with me now and let's have a look. Here are some equations for you, and right down below here, you can just see it sneaking through, are the solutions. So I want you to pause the presentation and have a go, and as you finish one, come down, look at the solutions, and then rewind and so on. You know the drill. Okay, so here we have question 1A and B over on the left there. And you can pause that and mark your work, got all the steps in there, and then C over on the right here, and then we'll come down to D. There we have it. So you can now toggle that back and go and have a look and finish those off one by one. I'm going to move on now, so here we go. All right, another question. Now this is what tests and exams in this subject like to have in them. How can you see it? There it is. It's an A. Consider that system. So let's construct a system that we can talk about and say, well, what happens if we play with the A value there? What happens? Okay, well, let's try and do the row reduction as usual in A land. Oh, be careful here. Okay, so here's our detached coefficients. That's okay. Now we want a 0 in this position, so here it is here. What are we going to do? Row 2, take 2 times row 1. There it is, just as usual. should be done separately in another line. Do the next one, but they've done it together, so let's go with them here. So row 3 minus row 1. So row 3 minus row 1 would give us a 0 there. Oh, now, how's your algebra? I hope you're okay there. Remember, algebra, as we talked about in that last presentation, part 1, introduces a letter to stand for a number. Don't be frightened of the letters. They're just numbers, so can we add them? Yep. Hang on in there, that's just a number. And now we want a 0 in this position, so we can see it's row 3, take 2, row 2. You can only play with these rows so that you don't disturb the zeros there. So it's row 3, take 2, row 2. Let's do it. Row 3's got an A plus 1. Take 2, row 2. Now just adding these here, how's your directed number work? A plus 1, take 30, is A, take 29. Okay, so what are we going to do now? Well, A could be anything. Let's discuss it. If A is not 29, if A is any other number, here it is, we would have 0x plus 0y plus 0z equals some number, if A is not 29. Okay, this is not possible. This is inconsistent. Impossible. Therefore, no solutions. Can you see what we're doing? We're doing the same stuff again, only we have the flexibility to talk about the possible solutions due to a changing A value in row 3. Okay, so if A equals 29, the last row is all zeros. What does that mean? Write it out. Rows are equations. 0x plus 0y plus 0z equals 0 if A is 29. This is okay. It's not impossible, but it means there is an infinite number of solutions. Why? Because the third equation has bombed. It's not producing any other possible information about our possible unique solution. So we're saying, hey, from that bottom row, Z could be anything. We can't find it uniquely and back substitute. But if we said it was anything, we could substitute it back into row 2, get a Y expression in terms of T, put it back in row 1, get X in terms of T, and we do see there is a set of solutions that follows that pattern. We just didn't have enough information to find a unique solution. Because that bottom equation bombed on us, we really do need now, how are you seeing it? We need 3 equations in 3 unknowns, all offering sufficient information to find a unique solution. Okay, so here we didn't. Our bottom equation, when we simplified them, gave us no further information. So we only have this pattern of the infinite solutions. But that is something. That is a bit of information about the system. All right, are you ready to work with algebra in this context then? Let's have a look now. Okay, so here's some questions. Let's do question 2, 3 and 4. Okay, so it gives you fairly clear instructions. You can see what's happening. They're putting a pronumeral in there, and sometimes in a couple of spots. Look at that. A, take 1 and A. Just work through it. Remember, algebra is easy for a person of your ability. Algebra, work with letters as if they are numbers. Work with letters, pronumerals we call them. Work with letters as if they are numbers. Don't get worried about it. What would you do if it was a simple number? Do it with your letter. So hang on in there with that one. Okay, so there's 2, 3 and 4. Might pause presentation, have a look at question 2. Then I'm going to take you down to the solutions. So we'll just go slowly to the next ones here. 5 and 6. 5 and 6 are fairly challenging questions here. Okay, you've got to remember the common denominator principle. That if you're going to combine equations and they have different coefficients in them, different row entries, to make them common, multiply one row by the number in the other and vice versa. You might just try and remember that. Okay, so let's go down and look at the solutions then. Okay, there's question 2 and part of question 3 there. Let's go down and finish off question 3. There's the rest of question 3. And question 4, see if we can get it all in. I don't think we can. Question 4, A, B and part of C. Question 5, same, A, B and part of C. Let's come down a little bit and try to get both of those C's. Yep, 4C and 5C. Yeah, it gets fairly messy in question 5 and 6. 5's getting harder. Okay, so coming down to question 6, down to the end of B, we go to C then. Okay, so 5 and 6 are quite challenging. Toggle back and have a go and see what you think. I'm going on now. Okay, so here we are, further applications. Okay, so what have we got? Well, I mentioned this in the introduction to this part. We have 2 equations as a 2 by 3 system, 2 equations and 3 unknowns. I think you can see now that what Hayes and Harris is saying is going to be true. You can see from our process of elimination, basically in the augmented matrix form, that you do need 3 equations in 3 unknowns to be able to solve uniquely for it. So we call this an underspecified system. There are less equations than unknowns, so you might have a little rule coming up. Now, if you have n unknowns, you'll need n equations to solve uniquely for it. Otherwise, you'll have information about the solution, but you won't be able to find a unique solution. So let's have a look at what we can do with this. So solving this system now. Here's our augmented matrix. We can get a 0 in this position by row 2 minus 2 row 1, and therefore we do have information, but not enough. What does that say there? It says neg y take 5z is 0. So y and z aren't going to be specified, so just let z be anything. Y then would be that, and you can back substitute into row 1. Remember, rows are equivalent to equations here in this augmented matrix system of solution that we've developed, and therefore we do have a pattern of the solution. The pattern of the solution is that there's infinitely many solutions, but they must follow these rules to satisfy the 2 equations that we did have. Because those 2 equations are telling us right up the top here. Those 2 equations are telling us a requirement on x, y and z. They can't just be anything. Okay, so now let's have a look what can be deduced up here in part B if the following equations added to the system. Well, now we can see back from the very beginning of this unit, if we had another equation, we can say our general solution here must work in that equation. So let's put, instead of x, the general relationship, instead of y, there it is there, instead of z, there it is there. And we find now we have a unique solution because we've added that extra information from another equation. Okay, and so we can state that we now have a unique solution. What if we added to that set this equation? Let's try it. There's what x and y and z have to be, the pattern to satisfy that original 2 by 3 system. Now we sub it in and we get 18. Oh, the t's all went out here. They haven't shown that. 6t, where are we? So we've got 6. Well, let's write this out again because this is not clear. We've got 6 plus 6t take 5t take 4t equals 18. Okay, so here, I don't know what they're doing here. We've actually got 6 to take 3t. We'll just get rid of this. 6 take 9 take, let's take 3t equals 18, I think there. Yep. take 4t. Yep. So this is actually neg 3t equals 12. So t is neg 4. So I think the book hasn't quite got it right here. They've got 6 equals 18, which is absurd. Now that is absurd, but that's not what we actually get here when we stick these values here. 2 plus 3t in place of that. Let's just check it. Plus neg 5t, and then t here. So just checking that, see that line there. Oops, no, I've made a mistake, haven't I? Let's go in here. This is 9t. Okay, that's better. Okay, so they are right there. 6 is equal to 18, just writing it out in full. So I wanted to check this. 6 plus 9t and take 9t, that's good. So that's okay. Just checking the work there as I did. Don't make that little slip here. 3 by 3 was 9t. Okay, so it is absurd. It is impossible. Therefore, there is no solution. So do you get the idea of checking solutions and adding an equation to it and seeing if that gives sufficient information to specify a unique solution? All right, let's come down now and have a look at some. So here's 9e, the first 4 questions, and they are just sort of general things. The idea is try to get the general solution to that, the general pattern. You know you won't be able to get a unique solution because there's only 2 equations, 3 unknowns. So get a general pattern and try to see what that last added equation will do for you. Will that produce a unique solution? And the same thing here. So just try to follow that. Can you see that these equations are these? And then you've added another one here, and to see if that improves your chances of getting a unique solution from the pattern you've got from the first 2. All right, then we've got a little bit of an economic model playing here, and seeing if we can use the information we're given to actually get an equation, or a 2 by 3 system here. So you need to think carefully what A, B and C might mean here. Okay, so here they are the coefficients, and you're trying to substitute values in for x so that you can get equations. All right, have a go. I'll just come down the usual way here. Question 5. Question 5. Then question 6 is a big one, so just come up here to question 6. Okay. I might have to toggle that a bit. Okay, and here's a question. Explain why those things. So you have to toggle that backwards and forwards. Maybe copy out the picture to get on top of that one. It's an interesting one now. You have to read that one carefully. And then in question 7, intersecting roads. That's an interesting application. Networking sort of idea there. And question 8. Again, a similar sort of question. Okay, so I'll come down to the solutions. Let's have a look at question 1. A and B. Question 2 and 3 coming up there. Let's just go down a bit. A, B and C. And question 3. Did you get question 2? There it is. Question 3. And then we'll go down to 4 and 5. Just come down here. 4 and 5. Question 4 down to D. Question 5, I think we've got a bit more. No, that's it. Okay, question 4 and 5. Question 6. Let's just go down a bit. Rest of question 7. Okay. All right. So Are you enjoying yourselves? It's getting interesting, isn't it? These applications are quite interesting. All right, toggle back and finish the questions and mark them. I'm going to go on now. Oh, here we are. Hang on, we've got question 8. Question 8. Nearly forgot that one. All right. Can it get any bigger and better? Oh, yes, it can. 4x4 and 5x5 systems. I just wonder, could you do it? 4x4 would look like this. These little crosses mean numbers, don't they? So this would be a 4x4 system. Let's get rid of this. So down here, that would be a 4x4 system. Would you like to do row operations on that? I don't think so. But what would you try to do? You would try to get rid of these and just have that one, wouldn't you? And up the next line, we'd have that much. And in the next line, we'd have that. So that you could use the same process. Solve here, back substitute, there's only 2 there, so get that. Solve for the other one, back substitute, back substitute. So can you see this augmented matrix approach is expandable to 4x4 and 5x5, etc. systems. An n by n system should be achievable where n is any real number by you, by creating all but 1 would be zeros there, and then doing the same procedure. All right, well, we're actually not going to do that. We're going to use technology to solve problems like that. But here's our elliptical path problem that was right back at the beginning. If you're into astronomy, have you got a telescope? No, well, bad luck. If you're into astronomy, you could use this general form for the ellipse now, and if the sun is at the origin, so we're looking at planets around the sun now, then if you observed on some grid system that these were the positions of the asteroid at certain times, then you could put those x and y values in and create a system of equations here. Can you solve those to find the coefficients in the equation of the general equation of the elliptical path, and therefore get a specific path for this asteroid? And of course we could use Equimode on the calculator there to do that, and it will go up to actually 6 unknowns of Casio. So remember, Equa, simultaneous, number of unknowns would be 5 here, and it will go up to 6. So we want 5 unknowns in this particular case, and then we enter the data and we solve for the coefficients. So that's handy, and that's what our elliptical path is looking like. And if we can find an equation, we can detect whether the asteroid will hit a certain point or whatever. And so coming down, putting the answer together, always remember, give a contextual answer. Don't state values only that we have calculated. Put it all together. We wanted the equation, so put the answer in the context. Okay, so that's the elliptical orbit in full with the coefficients in there. Do you want to try some applications now of linear equations of a higher order, 4x4 and 5x5? So come down and have a look at 9F now, the first 3 questions. It's your job to actually introduce a pronumeral here for the number of things. I don't know what you might do. You want to use A, B, C, X, Y, Z, whatever, for these footballs, netballs. There's a bit of a puzzle problem here of how many has each school got. And then there's one just like we had before, completing an equation that's given to you by substituting points in, and getting undetermined coefficients there, and then there's another asteroid problem there. Alright, so have a look at those, and the same procedure as before. Stop the presentation and have a go and come on down to find the solution as you go. So here we have 4, 5 and 6. I think that's the last one there. 4, 5 and 6. And so pause that, and then we'll go down and have a look at the solutions. 1, 2 and 3 there, left and right. And can we get 4, 5 and 6 on? I think we can. Yep, 4, 5 and 6. Can you see the possibilities here? I want you to think particularly about the expandability, how you can expand this matrix approach, this array approach. Never forgetting though that in this context the rows are equivalent to equations. So if you get stuck, write out that last row and have a look at it. Alright, good luck with that. You're doing well. You've come a long way now. I hope you're enjoying the skills you build up. And we'll go on with other uses of matrices other than solving systems of equations in further presentations. So I hope to see you then. Cheers for now.